What's up, everybody? It's Dan, and we are back with more of the review sheet, which is fun. So, problem number 31, find the derivative of this whole thing. Okay, so it turns out these are not that bad. Not that bad. So, g prime of x, well, it's going to equal, if you have x on top, okay, if you have just an x on top, all you have to do is substitute x in for the variable. In this case, it's t. So this would just be 1 plus x cubed to the fourth. And you are actually done, okay? Taking the derivative is the inverse operation um, of taking the integral or the antiderivative. So for that reason, we can substitute that x in here, and then we would call it a day, actually, okay? Now, I will tell you, for my student at home especially, I would caution you that things get a little weird though when you have something other than just an x here. For example, on the next problem, there's a 3x, right? That is a situation where things are pretty much the same, but there's like a little extra tweak you have to do. It's also going to be different if the x is on the bottom and there's a number up top. Then there's going to be a little tweak that you have to do, which we're going to go over. And there's also sort of a third weird situation where you have an x on the top and the bottom, which we're going to go over. So that requires a tweak as well. But the bottom line is, anytime you have just an x on the top, it's just going to simply be a matter of substituting. All right, so that's how it goes. G of x is this, but g prime of x is this. So that's that. Okay, with regards to the next one, f of x equals blah, blah, blah. Okay, so what we have to do here is we will have to split that into the following situation. The first situation, we're going to have 2x down below, because it is down below, but it's going to go up to 0, or some number like 0. Okay, it actually doesn't matter, but we're going to use 0. And then we have the u squared minus 1 u squared plus 1 du. And then we're going to be adding with 0 on the bottom, going all the way up to 3x. All right. So that's what you have to do when you have the variable present on the top and bottom of the bounds there. And then we can look at this one, and you might be tempted to just substitute 2x in there, but it is a little more complicated in the sense that you want the variable thing to be on the top. Now in this one, it is on the top, so we're actually happy with that, and that's going to be a little bit more like easier, I would say. This one, the variable's not on the top, so you're going to have to do an extra trick here, and the extra trick is to factor out a negative, and that will actually switch them, okay? So that's going to switch them. And then we still have this scenario, which is, what we want. So make no mistake about it. This is the same thing as that. It's just written in a different way and in a way that will enable us to do that substitution that we've been talking about. Now, speaking of the substitution, this time we could be substituting a 2x in there, and in fact we will. But this will result in a chain rule situation. Anytime it's not just x, you're going to have to not only substitute that in there, but you're also going to have to multiply the result by the derivative of this thing, okay? So let's kind of go ahead and do that now. It's going to be negative something squared minus 1 over something squared plus 1. And that something is going to be that 2x, right? So we have 2x. But now we have to do the additional thing of multiplying by the derivative of 2x. And the derivative of 2x is just 2. All right. So it's going to be that plus the exact same protocol over here. So we'll keep it in, we'll have this in red actually. So it's going to be something squared minus 1 over something squared plus 1. And what do we substitute in there? Well, it's going to be 3x. And then, as you would probably guess, we're going to have to multiply that result by the derivative of 3x, and the derivative of 3x is 3. So what does that turn into? Well, first of all, we're going to have 2 times the entire numerator, and in fact, you could say it's negative 2 times the entire numerator, but I'm going to keep the negative off to the side because it just kind of looks better. So we're going to have 2 times whatever that numerator is. Now, that numerator is 4x squared minus 1. And then down below, we have 4x squared plus 1, okay? Now, could we distribute that? Sure. It's often the case that a lot of calculus teachers will be fine with just leaving it like this because they have mercy in the sense that they don't need you to just multiply everything necessarily. Over here, we will have a similar sort of structure where it's going to be 3 times, in this case, 9x squared minus 1, and then that's all over 9x squared. I didn't really need the parentheses. Let's see, that's going to be all over 9x squared plus 1. So that is how you do that one. Okay, so problem number 33 is a little bit challenging because it's actually like a chain rule situation because it's the same situations we've been dealing with, except there's this exponent of 3, which means there's sort of this extra layer of complication. Now let's forget the problem and let's focus on a simpler case. Imagine you had something like x cubed plus 2 squared, okay? Well, in that case, or actually we'll make it to the 20th power. How about that? So imagine it was that. And what would you do in that case? Well, some students would be like, well, I'll just multiply the binomial 20 times and then apply the power rule. And everyone knows that would be a terrible idea because that would take forever. But what you can do is you can use the chain rule. Now, the chain rule is essentially a way of acknowledging that what we're really dealing with here is something raised to the 20th power. So imagine I had a raised to the 20th power. Imagine we were trying to find the derivative of y with respect to a. Well, what would you do in that case? You would just bring the 20 out front, and then you'd have a 19 there, okay? That's what you would do, okay? Well, in a way, you can kind of do that here. You just have something raised to the 20th power. So what you could do is you could put the 20 out front, rewrite this thing, and now it's to the 19th power, right? You just rewrite it and raise it to the 19th power. That's what we did here. We rewrote a, we raised it to the 19th power. However, with this case, since there's a bunch of gobbledygook in here, you're going to have to do the additional step of multiplying this by the derivative of what's inside the parentheses, okay? So it takes a while to get used to it, but this would be 3x squared, okay? That's what you'd have to do. Now, you might be wondering, well, why didn't you have to do it here? Well, actually, we did do it here. It's just that you don't see it, okay? Every time you use the power rule, it's actually secretly the chain rule, okay? Because the 20 goes out front, it becomes a 19, and then you multiply by the derivative of this, the a. Well, what is the derivative of just a? It's 1. So the truth is that even when you're using the normal power rule, it's always the chain rule. So you're always doing the chain rule, okay? It's just that in this case, the derivative of a is 1, so we don't typically write that. We typically just write, 20a 19, and then you're done, right? Well, in this case, the derivative of this is not 1, it's 3x squared, so you have to take that into account. But the bottom line is, in a relatively simple case like this, notice how it's always a matter of putting this out front, preserving this. Notice how I rewrote it, right? I didn't mess with it. I rewrote it. I raised it to 19 instead of 20 this time. But then on the back end, I multiplied by the derivative of what's inside. So that's the pattern that we're going to embrace now, okay? We're going to embrace that pattern now. And in case you would like this as a reference, something to compare what we're about to do to, I'm going to leave it. So we're going to go on this journey. The original thing, which I'll just write, is this. T cubed plus 1 to the 10th dt raised to the third. Okay, so notice how it's this whole thing raised to the third. So we're going to do a chain rule. We're going to bring the 3 out front. When we do the derivative, we're going to do the 3 out front and then bring it down to a 2. So what goes inside here? The original thing goes inside here. That's what happened here. What goes inside the parentheses? The original thing. It's right there. Okay, so it's the original thing goes inside. So that means you're bringing the integral symbol and everything. Okay, including the 10 and the dt. All right, all of that is intact because the truth is that's just some value. It's basically a number. It looks weird, it looks terrible, but it's a number. You know, if we knew what x was, then we would certainly know what it is, right? Now we don't know what x is, so we're kind of stuck with it. Okay. So anyway, we did the same thing, but what do we do over here? We had to multiply now by the derivative of what's inside. So then the question is, what's the derivative of what's inside? What's the derivative of all this black ink here? What's the derivative of that? That's the question now. Well, the good news is the derivative of the integral of this is nothing more than plugging x in for t. Okay, so that's all we're going to do. We're going to put brackets here, and we're going to replace t with x, and it's just as simple as that. And we still have even the 10 there. Nothing's changed about that. Remember, finding the derivative of an integral, as long as there's an x here on the upper bound, is really easy. You don't even change anything. You just put the x in for t, and there we are. So that's the answer at the end of the day. Now, I'm very like trigger happy when it comes to the brackets and the parentheses and all of that. So we don't really need those brackets there. But that's the answer right there. Now, some of you might be like, but what about this? Shouldn't we solve this? Well, no, we should leave it alone. Okay. The answer is no. Just leave it alone. We don't know what x is. Okay, we don't know what x is, so we're stuck there. All right, so that's how you do that. Okay, so problem 34 asks for the average value of the function f of theta equals this on that interval there. So for my student at home, just remember the average value of a function. Imagine you had a curve. Well, there's some value here that represents the average value of a function. We call it c. And it is such that the rectangular form on a particular interval there, the area of that rectangle rather, would actually equal the area under the curve, which is in red. Okay. In that interval there. Okay. So there's some value where the rectangle formed there, the height of the rectangle, would result in the area of the rectangle equaling the area under the curve. Okay, and that what we're doing is we're finding that. Okay, so the way to do that is really not that bad. I mean, it is kind of just a matter of remembering the structure of what you have to do. And the structure of what you have to do is to remember that is the average. It's going to be 1 over b minus a all over b over a f of x dx. So it's actually just as simple as that. Okay, if you can remember that, it's like to take the integral, but also make sure that this is out front. Okay, now b and a have to do with this interval, so b in this case would be pi over 4, and a in this case would be 0. I'm seeing the necessity of bringing out the handy-dandy reference guide for the trig integrals. And here it is. Okay, so here is the reference guide for trig integrals, and I could already tell we're going to be using this one. Okay, it's actually going to be nice. It's going to be pretty easy. So I say we do it. Let's do it. We're going to have 1 over b minus a. Well, b is pi over 4 and a is 0, so that's going to be pi over 4 minus 0, aka pi over 4. We'll worry about that later. And that is such that we're going to have pi over 4 up top. We're going to have 0 down below, and then we're going to have this thing, secant theta, tan theta, d theta. Now, let's just get this over with. 1 over pi over 4, do you understand that that's just going to be 4 over pi? Okay, pause the video, think about it if you have to. I'm going to get this over with. It is 4 over pi. It's better to think of it that way. Let's just get that over with. And I think you're going to be pleasantly surprised how easy this is because, I mean, really, it's just 4 over pi times, well, what's the derivative of this? It's right here, right here. It's secant, okay? Secant of theta, and with, you know, the pi over 4 and the 0. So I do believe we are probably going to need this unit circle soon because I really like to memorize stuff. I mean, maybe I should, but I like to rely on these reference guides when I can. I also sometimes forget stuff. So I think everyone would agree that what we're really dealing with here is going to be 4 over pi times secant of something minus secant of something else. Well, it's going to be pi over 4 here, and it's going to be 0 here. So on the next line, we are looking at 4 over pi times, well, what the heck is secant of pi over 4? Well, secant is the reciprocal function of cosine. So what we could do is we could find cosine of pi over 4 and then flip it upside down. So cosine of pi over 4, pi over 4 is right here. The cosine is radical 2 over 2. It's the x-coordinate. Cosine is the x-coordinate. So we're going to take that radical 2 over 2. We're going to flip it upside down. We're going to get 2 over radical 2. And after rationalizing the denominator, it's just going to become radical 2. Now, in case that's not clear, flipping it upside down, you'd have to rationalize the denominator. And can you see how that would result in this, which would result in canceling, and then we'd be left with just that. So there it is. Now, secant of 0, well, cosine of 0 is 1. So 1 flipped upside down is just 1, right? So it's going to be minus 1. So radical 2 is irrational. Pi is an irrational number as well. So the answer, you know, probably I think the teacher would be okay with 4 radical 2 over pi minus 4 over pi. I think that should be fine. And don't be surprised if there's just, you know, also 4 times this quantity with the pi underneath. So either way, this is the correct answer. Different professors have different preferences with regards to how to leave the answer. And textbooks sometimes differ in that way too. So anyway, this is how you do it for sure. And moving on. Okay, so problem number 35 essentially is asking the same thing as problem number 34, except they're asking for one more step. So first of all, they're asking for the average value of the function similar to problem number 34. Now that's going to give you a y value, okay? However, in this problem, they're also asking for what's the x value that corresponds with that y value. So it's perhaps the case I did not make it as clear as I could that in the previous problem, this produces a y value, okay? And that's what we're going to do here. It's going to be the average y value. And then at that point, we're going to find the x value, they call it c, that corresponds with that y value. So it's going to be pretty easy. We just find the y value like we did before, and then we're going to plug it into the original function. So we are going to embark on the exact same journey. Therefore, it's going to be 1 minus b, 1 over b minus a. Now, b in this case is 4. So we can say 4 minus 0, that's fine. We're going to have 4, we're going to have 0, we're going to have radical x dx. Now, obviously, that is going to be 1 over 4 times the integral. And x, radical x, could be written as 1/2, x to the 1/2. So then we're ready to go on our journey. We're going to be taking the integral of that. It's going to be this. And we're looking at 4 and 0. So the good news is whenever this is 0, it makes our lives a little bit easier because when we plug in 0, we're going to be just having a 0 here. And it's going to be 2/3, 4 to the 3/2 minus 0. So we could sort of ignore the 0. I always like it when that happens. Had that been another number like 1, unfortunately, we would have had to substitute that in and perform the subtraction. So really what we're dealing with is 4 plugged in for x. Now I'm going to represent this as the square root of 4 cubed. Okay, that's, the reality of what's happening here. It's going to be 4 raised to the 3/2, so that's really the square root of 4 cubed. And that will become 1/6 times 2 cubed, which is 8, and that is 4 over 3. So that is the average value of the function on that interval. And then we want to find c such that the average value equals f of c. So in other words, take that 4/3 and set it equal to the function. And the function is this. And all we'd have to do here is square both sides. And in doing so, we would have 16 over 9. So that is the answer there with regards to the x value. That's the average y value. That's the x value that corresponds with it. So that is how you do that one. Okay, so, this one certainly looks like a U substitution one. Certainly looks like it. So we're going to find out. We are going to find out. Let's see. Okay, so I think it's worth experimenting and saying that U might be radical x, and that's secretly x to the 1/2. So therefore du would be 1/2 x to the negative 1/2 dx. Hopefully this works. Not really sure it's going to work just yet, but maybe it will. And then it would be like 1 over 2 radical x dx, and then there would be du, and then at that point we could, here's the way I like to do it. I like to solve for dx, actually. That might be a little different than the way some teachers do it, but if we were to get that dx by itself, it would be 2 radical x du. So let's see if that helps. Let's see if that helps. Well, if we were to rewrite it with u inside, everything would be cosine of u all over u. And instead of dx, it would be 2 times x du. So typically what we're used to seeing is that you should be able to cancel this with like something, right? The problem is it doesn't look like there's any opportunity to cancel this radical x because at the end of the day, when you do U substitution, after substituting back in, you want to just have u's and all the x's need to be gone, essentially. But here's the good news. We already established that u is equal to radical x. Therefore, anytime you see a radical x, well, you could just replace that with a u. So the truth is that I could have said that dx equals this, sure, right? But really what I could have said is that, okay, well, dx is equal to 2 times u du, right? So therefore, I can replace this also with a u, okay? So that's an interesting one. I mean, I feel like this one's kind of tricky for that reason. We have to really be on guard. So I guess maybe the moral of the story is, if you don't see a cancellation right away, go back and look and see, look at what you're substituting and see if there actually is an opportunity to cancel. Maybe you didn't see it the first time around. So this 2 could now go on the outside. So the truth is it's going to be 2 cosine u du. And the integral of cosine, according to our chart, is just sine. So this is going to turn into 2 times sine u plus c. But we already established what u is. U is radical x. So it's equal to 2 sine radical x plus c. So that is the answer.